So let's talk a little bit about kinetics and radioactivity. And all radioactive decay follows first order kinetics. And kinetics is, right, how fast or slow a reaction takes place. The good news is it really is the same sort of kinetics that you learned in the kinetics sort of chapter. They will use some different sort of symbols sometimes because it's nuclear chemistry, but it ultimately is the same two sort of equations. To remind everybody about the two equations for first order kinetics, that basically means that you take the natural log of A is equal to the natural log of A naught minus KT, where the half-life is the natural log of 2 divided by K, which is the rate constant. In here, they will use some different symbols sometimes, like you can see on the bottom there. They'll use N for nuclide instead of concentration. They will also sometimes use K. They'll also sometimes use the lambda symbol for the decay constant. They call this the decay constant in nuclear chemistry, but it's the same thing as the rate constant in kinetics. And a reminder that when we see T here, that's actually time. Yeah, so that's not temperature, but that's actually time. So again, sometimes even the decay constant is a lambda sort of symbol is sometimes used for it in nuclear chemistry because they like to use their own sort of things. All radioactive decay follows that first order kinetics, which means if you take the natural log of A versus time, you will get a straight line where the slope of that line is equal to the rate constant or the decay constant in this case. And that is because if you rearrange the first order equation, natural log of A is equal to minus KT plus the natural log of A naught. This is written in the form of a straight line, y equals mx plus b, where on the y you put the natural log of A, on the x you put time, basically. And the slope there will equal negative, again, of the decay constant in this case, which is really very similar to the rate constant. It's kind of the same idea. Also a little bit different than sort of traditional kinetics. In traditional kinetics, when we put our values into this equation, which is sometimes referred to as the integrated rate law, we oftentimes use molarity and concentration, which you can still use. But in nuclear chemistry, we do use a lot of different sort of units. And it really doesn't matter the units that you put in here, as long as they're the same unit. So you can do like grams and grams on both sides. You can do milligrams and milligrams. You could also do rates of radioactive decay, like counts per minute or something like that, is sometimes used. By the way, this first A is the final concentration. This A with a naught is the initial, yeah, concentration. And again, the K is our decay constant. This is also sometimes written 0.693 because that's what you get when you take the natural log of 2 on your calculator. Yeah, so that is the same thing. Half-life, right, is the time it takes for half of whatever you started with to go away. Yeah, so if you had 10, the time it takes for you to end up with 5, and after that, the time it takes for you to end up with 2.5, and then I need a calculator after that point, but I keep going by 2, and you could cut it down. Any questions on that there? All right, so there again, like I said, sometimes they will use these N's for nuclides, and again, that is the decay constant, and which is basically kind of, again, the same thing as the rate constant. This is also a common graph for first order kinetics, and what we see is over time it is decreasing the concentration of our nuclei, which is what we expect because it's decaying, right? So we're losing it over a period of time. Now, these are some half-lives of some various nuclides, and as you can see, half-life, which again is that time it takes for half of whatever you started with to sort of go away, can be really long, can be really short. Clearly here we have uranium-238, which is like 4.5 times 10 to the 9 years, which is a super long time for one half-life basically to occur. Unfortunately, I don't think any of us will live through one half-life, right? Carbon-14 is 5730, but there are some half-lives that are obviously very quick. As you can see there, 55.6 seconds. It's like every 60 seconds, half of it's gone. So it goes away very, very fast. As we'll talk about a little bit later on in the chapter, obviously, if you're using anything like for medicine, right, you would want a very short half-life. For example, it does vary even depending on the type of isotope that you're using. Different isotopes, even of the same element, are different. For example, copper 64 is like 13-hour half-life. Copper 68 or 68, I think it was, it's like 3 days. So there's a big difference in terms of how long that takes for it to go away. Usually about 10 half-lives, you're gone. Yeah, not too much left at that point. All right, so let's try a little kinetics here. Activity, if you have 1.35 milligrams of plutonium-236, calculate the mass that will remain after 5 years. Give you some info there. Our half-life of Pu-236 is 2.86 years. So let's see what you come up with. Yeah, you're doing so here. Anything that involves sort of how long something takes to decay and all that's going to be kinetics, and it's going again to be that first order kinetics, which if you want, you could just use the regular sort of first order equation. Don't necessarily have to use the nuclear chemistry version of it. And you also want to think about the half-life equation. Sometimes they are oftentimes kind of used together, especially in these type of problems. And that is because if we sort of label up what we got going on here, we have an initial sort of concentration, if you will, of 1.35 milligrams. We want to know how much will remain at the end. So that's like your final concentration, which you don't know, after a time of 5 years. Now, if we look at our sort of first order equation, we can see that we have everything that we need except for actually a couple of things. We are looking for this guy. We do have this one given to us. We do have this one, but very common in these problems, you are missing the decay constant here. And that is where the half-life equation is going to come into play because we have the half-life given to us. So using the half-life equation, which is the natural log of 2 divided by the decay constant, we could actually solve for K, which is sort of missing here. And to do that, K would equal the natural log of 2 divided by the half-life. And I'm going to put this in, and that's going to give me the natural log of 2 divided by 2.86 years. That's going to be the natural log of 2 divided by 2.86. That's going to give us a K value here of 0.242. The units here are actually 1 over years. And by the way, for first order equations, the decay constant is 1 over seconds, 1 over unit of time, basically. So it's usually 1 over some type of unit of time. This is also where we want to make sure that our time, which is in years, and our decay constant, which is also in years, are the same units. It's very common as well that they are in different units of time, so you have to do some type of conversion sometime. In this case, we don't have to because they are both basically in years. So now we have everything we need to actually go in here. So the natural log of A, which is what we're looking for, would equal the natural log of our initial concentration, which is 1.35, minus our decay constant that we just solved for, 0.242. Again, 1 over years is the units. And that's going to work good with our, not 2, but our 5 years. This way the years will cancel out. So again, that's really important, those two guys in terms of those units, to make sure they agree. I'm going to clean up everything on the right-hand side of the equation. Basically going to take the natural log of 1.35 hit equals subtracted, open some parentheses, 0.242 times 5 hit equals. Going to give me a natural log of A is equal to minus 0.9099. Yeah. Any questions so far? To get rid of the natural log, we got to take the e of both sides there. So we're going to e this guy, and we're also going to e this guy with whatever sign it may have. When we do that, those guys go away, and we end up with a. And in this case, we end up with, I'm not going to use the rounded number, I'm going to use what's in my calculator, and we end up with something like 0.403 off of the non-rounded number. And the units here would be the same units as our other guy, which would be milligrams in this particular case. First off, any question on the calculation? Does make sense because at the end of 5 years, this thing's decaying. We should end up with less than what we started with, right? So again, if we ended up with more than what we started with, something not so right in terms of the math. And it's about 2 half-lives, I guess, it went through maybe-ish, or just under that. So if you divide it by 2.6 and divide it one more time, just less than that. Second half-life, we're in the right ballpark, probably. Yeah. Any questions on that one? All right, then why don't you try the next one and see what you come up with here. Let's do a little radon 222. Assuming no loss from leakage, if there's 10.24 grams of it in the house today, how much will be there in 5.4 weeks? And the half-life is 3.8 days. Let's see how we're doing here. So again, we're going to use our kinetics equation here. So once again, our two that, again, oftentimes will kind of go together is our first order, and then obviously our half-life here. We're going to run into kind of the same situation as we did on the previous one. We're going to have enough information, but we're still going to be really missing our decay constant in this case. We do have our initial concentration of 10.24 grams. We are, again, looking at basically how much will be there when it's all said and done. In this case, our time is 5.4 weeks. And again, we have the time, we have that, we are looking for that. So once again here, we are missing our decay constant. So that is where the half-life is going to come into play. We do have some unit issues here. We have this time in weeks. This one's in days. At some point, you got to do a conversion. So I'm going to leave this in days, but I'm going to convert my weeks into days so everybody's on the same units. Again, if you did not do that, then you're going to be off because your units won't be the same. So I think still in 1 week, there should only be 2 days. No, there's 7 days, I think. So if we convert our 5.4 weeks into days, looks like we got like 37.8 days. So now both of my units of time are in the same kind of unit, so I'm okay. Again, if you did weeks, you'll have slightly different numbers, but at the end, it should really be the same-ish answer there with some rounding and maybe a little bit different. So solving for decay constant to be the natural log of 2 divided by our half-life, which in this case is going to be 3.8 days. That's going to give us the natural log of 2 divided by 3.8. That will give us a decay constant of 1.182. Again, the units here are really 1 over days or reciprocal days, however you want to do that. Now that we have that, we're good to go back into this equation. So natural log of A is going to be our natural log of our initial 10.24 minus our 0.182, basically 1 over days, and that's going to be times our 37.8 days. And again, this is why the units are important, that they are the same, so everything cancels out correctly. So cleaning up the right-hand side here, 10.24. Natural log 10.24 minus 0.182 times 37.8. Going to give us a natural log of A is equal to minus 4.553. At this point, we're going to take the E of both sides here, and that's going to cancel those guys out. And again, we're not going to change any signs or anything like that. It's just going to leave it the way it is, and we'll call it 0.011 grams in this case. Any questions on that? That is less than what we started with, which I guess is good. Yes, I suppose in that case. Any questions on first order kinetics or half-lives or any of those things there? All right, then let's talk a little bit about, we could also use sort of our kinetics here to figure out, this one we just did, yep, okay, wait, there's another one. We can also use it for things like radio dating, or radioactive dating, by basically figuring out, for example, how much carbon there that we had, how much nitrogen may be left over. In the case of uranium dating, we could figure out, basically how much lead we have from there as well. We could still use our regular sort of kinetics equations to figure out, how old something is. We would be solving for the time usually in that kinetics equation. So a lot of times if you're doing some type of radio dating, you would use your first order kinetics, and usually if you want to know how old something is, that would be what you would be solving for. Again, just like the previous problems, you will oftentimes be using these guys here together, as you might be missing the K as well. So let's take a look at one here and talk about sort of how to approach this. An agent skull gives 4.5, and the units there are actually disintegrations per minute per gram of carbon. So it's actually a rate of radioactive decays, what we're looking at there. It's actually not Celsius there on the bottom or anything like that. So it's actually disintegrations per minute per gram of carbon, which is a rate of radioactive decay. And as I mentioned earlier, you can still use your kinetics equation with things like radioactive rates of decay in there rather than, say, molarity or grams and stuff like that. A living organism gives 15.3 disintegrations per minute per gram of carbon. We're looking to figure out how old this sort of skull is. The importance of this is it is carbon, so we actually want to use the half-life for carbon that we saw on the previous slide there. I think we might have it here or not. It is right there. We would want to use 5730 for our half-life in this case. So if we did this, we would still approach it the same way. We're going to use our first order kinetics equation. We're also going to perhaps use our half-life equation. And in this case, we have a couple of things. We have an ancient skull, so that's kind of like the dead guy, right? So that's the end of the road. And a living would be kind of like the beginning of the road or the initial there. And again, here we are looking for how old this thing is, so we're looking for time. So we are missing our decay constant in this case. So we are going to use the half-life there of carbon 13 or 14. And we're going to solve for K. So K in this case would be the natural log of 2 divided by the half-life. And again, because it says grams of carbon in the units there, that is how we know we should use our carbon's half-life. And if we do that, we get a natural log of 2 divided by 5730. Going to get us 0.000121. The units here are 1 over years. And now that we have that, we do have everything that we are looking for in this case, except for time, which is what we're trying to find out, which is how old this guy is. So the natural log of our final spot there would be our guy with our smaller disintegrations, equals the natural log of 15.3, which is our initial, minus our K of 0.000121 reciprocal years. And again, here we're trying to figure out how old everybody is in this case. Me personally, when I would do this is I would just simply take the natural log of 4.5, hit equals, and then I'm going to basically subtract this guy to the other side. So I'm going to subtract the natural log of 15.3. And when I do all that, I will end up with a negative 1.2238 equals minus 0.000121 reciprocal years in my time. At this point, all I have to do now is divide everybody over here, including the negative sign. So we're going to divide 0.000121. Going to give us a time of 10114 years old. That's pretty old. That's about 10,000 years old. So I would say that would qualify as being ancient. Yeah, in this case. So this, again, you can use that sort of rate of radioactive decay in this equation. You could really use anything as long as these units are the same. So it didn't really matter what they were, but they were the same on both sides. You obviously cannot use two different types of units on both sides. They got to be the same unit. Any questions on that there? All right, I did one, you do one now. So I want you to do the next one. I think we're looking for how old is a piece of rice that was found somewhere, I think, in this case. Let's take a look at it here. There it is. So we have dated the civilization to 15,600 years ago. If a living sample gives 20 counts per minute per gram of carbon, again, that's another unit of radioactive decay, what would be the number of counts per minute per gram of carbon of a rice that was found on the site here? So again, since it is carbon, we're going to use the same half-life as we used in the previous problem there, which again is our 5730. So we're looking for how many counts per minute per gram of carbon will this really old piece of rice give? Okay, let's take a look. So here we have something that's really old. We want to know what kind of counts per minute our radioactive decay is it going to give. So in this case, we are going to use our kinetics equation here. And since we've had to use it for the other ones, I anticipate we probably will still use it here, the half-life equation as well. All right, so in this case, we are given the time, which is 15,600 years. We are giving a sample that's living, so that seems like initial. And we are looking for what the counts per minute will be, which is our final. So once again here, we do need to count our K, and it will come out the same as the previous problem, as it is still carbon, and we're using the same half-life, obviously. So our K here, once again, will be the natural log of 2 divided by 5730 years. And I believe that was 3 zeros and a 121, I believe, if I remember correctly there. All right, so now that we do have K, once again, we could clean up everything on the right-hand side. So that's going to be the natural log of A is equal to the natural log of our initial counts per minute per gram of carbon, which is 20, minus our K that we found, which again is reciprocal years, and the time in this case, 15,600 years. We're okay in terms of units. Again, we have them in the same unit, so that is always a thing that you want to look at. So we're going to do a little natural log of 20, hit equals, minus it, open some parentheses, 0.000121 times a 15,600. Going to hit equals, going to give us the natural log of A is equal to 1.108-ish. We're going to get rid of the natural log of both sides once again by taking the E of both sides. That means that we will end up with, and I'm not going to use the rounded number here, I'm just going to use what's on my calculator, approximately 3.03. The units here will match the initial units, so these would be counts per minute per gram of carbon. or I guess you could just write counts per minute per gram of carbon as well. No. That is less counts per minute than we started with, which should be good, right? Because as something is decaying, right, it's sort of dying in that sense. It's not going to be giving off as much, obviously, radiation at that point because it's gone through several half-lives, perhaps. So the counts per minute per gram of carbon should be less than, obviously, what we started with. Any question on kinetics type of questions? Now you should be able to answer how old your in and out double is on the exam next week, and we should be good, yeah. All right, any questions on that there? All right. So next thing we're going to talk about is fission, and fission is the process where a sort of unstable nucleus will continue to basically fall apart, if you will, go through decay, and it will form two new nucleuses. And the process of that usually is this guy will kind of fall apart into two new nucleuses, will also give off some neutrons, and a lot of energy is usually the process there where something will be given off. So during nuclear fission, there is sort of a slight difference in the mass of basically the nucleus of the new guy and basically the protons and neutrons that make it up, which are the nucleons. So there's a slight mass difference between basically the protons and neutrons that make up the nucleus and what is formed as a result of sort of the fission reaction. And that slight difference in mass gets converted into energy really through our good friend Einstein and his equation, E equals mc squared. That is energy, that is mass, and that is the speed of light, which is 3 times 10 to the 8 meters per second in this particular case. So in our case here, what we're going to talk about is what is referred to sometimes as the mass defect. And that mass defect is that little bit of mass that gets converted into energy in this process. And in a fission reaction, it obviously gives off way more energy than any sort of exothermic chemical reaction. So as you can see, there's a fission reaction, for example, like what they use in, say, nuclear power plants, give off somewhere by 10 to the 13 joules of energy. As a comparison, you know, your really super exothermic reaction is like 10 to the 6 joules of energy. So there's a lot more energy given off in a fission reaction. Now, that mass defect, as I mentioned a second ago, is again really the mass is going to be kind of converted into energy through this process. And the energy that's released when we do form that nucleus is sometimes referred to as binding energy or nuclear binding energy. And there are a couple of conversions here that can be helpful when we do these type of problems, and they're really kind of based off of the E equals mc squared. You could actually use kind of the conversions, or you could use the Einstein equation there. 1 mega electron volt is equal to 1.602 times 10 to the minus 13 joules, and that is your sort of conversion between two very common units of binding energy. So binding energy a lot of times is given in mega electron volts, or is given in joules, and those are two very common units that are used. It's also a lot of times given in mega electron volts per nucleon or joules per nucleon, which is a measure of stability. So sometimes people use binding energy per nucleon, and you could use it as a measure of stability. The higher the binding energy per nucleon, the more stable something is. 1 AMU mass defect is equal to 931.5 mega electron volts. That's another sort of conversion. And again, you could either do it kind of through the conversion way, or you could use the Einstein equation, and they both will give you kind of the same answer. You usually will end up in sort of joules if you go this approach. You'll oftentimes obviously get to mega electron volts here, but you can also get to joules as well using that conversion if you wanted it. So let's take a look at sort of what we're talking about here. So the nuclear binding energy, again, is that energy is required to break up a nucleus into its components. So if we took something like fluorine 19 here, it has basically 9 protons, as you can see there, and if we take 19 minus 9, will give us 10 neutrons. So the first thing that we could do is actually calculate the mass defect here, and if we have this fluorine 19, and it has an atomic mass of, we'll call it 18.9984 AMU, atomic mass units. If we were to calculate the mass defect here, we would take basically the 9 protons and we would times it by the atomic mass of a proton, which is 1.007825 AMU. We would then add it to 10 times the atomic mass of a neutron, which is 1.008665 AMU. We would then actually subtract it from the fluorine 19 atomic mass of 18.9984 AMU. So we're basically taking the mass of all the protons, taking the mass of all the neutrons that are in the nucleus, which is basically the nucleon and make up the nucleus, and we're subtracting from the atomic mass of that isotope. And if we do that, we will end up with here. We will end up with a mass defect of 0.1587 AMU. That is the basically difference of mass between basically the protons and neutrons that are in the nucleus and the mass of the actual isotope itself. That little mass there is going to basically be converted into energy through this process. And again, at this point, you have a couple of things you could do. You could use E is equal to mc squared. And if we did that, our mass would be our mass defect in this case. This gives you 0.1587 AMU times 3 times 10 to the 8 meters per second, and that's going to be squared. And if we do that, we will end up with here 1.43 times 10 to the 16. My units here are actually AMU per meter squared divided by second squared. One relationship that you might remember is a joule is equal to a kilogram times a meter squared divided by second squared. So that is the same thing as a joule. We are almost there, except that we are at AMU and not kilograms. So you could take this and do a conversion to convert us into kilograms. And we can use our good friend, Mr. Avogadro, perhaps, yeah. So that's going to be 6.022 times 10 to the 26 AMU is a kilogram. Avogadro's number is to the 23rd. Yes, to the 26 gets you kilograms, to the 23rd gets you grams. Yeah, so that's why it's to the 26 here. And that will get us the AMU to cancel out. And if we do that, we will end up with 2.37 times 10 to the minus 11. And that would be kilograms meter squared second squared, which is the same thing as a joule. Any questions first off on that there? Now, that would be technically the binding energy, but typically it's given, as I mentioned, in joules per nucleon or mega electron volts per nucleon. So basically, a nucleon is the protons and neutrons. I guess that's a fancy name for mass number. Yeah. So we're going to basically take this and divide it by 19 nucleons, which is basically its protons and neutrons. And if we do that, it will give us a binding energy of 1.25 times 10 to the minus 12 joules per nucleon here. Any questions on that there? Now, if we wanted to, we also can convert this into mega electron volts at this point by using that conversion that there is 1.602 times 10 to the minus 13 joules per 1 mega electron volt. And if we wanted it in sort of the other unit that's commonly used, we could do that, and we'll get something like 7.791 mega electron volts per nucleon here. So those would be the answers in both units. First off, any question on that calculation? Now, we could, if we wanted to, just straight up use those conversions rather than Einstein's equation. And those conversions I'm talking about, which were on the previous page, we could have actually just picked up with our AMU, which was 0.1587 AMU. And we could have done that 1 AMU is 931.5 mega electron volts, which would have gave us 0.1587 times 931.5, gave us 147.8 mega electron volts, which if we divided it by 19, will get us 7.780 with rounding, a little bit different, but pretty much the same number as kind of what we got going on down here. So a little bit different with rounding, but you could have went that approach. And obviously at that point, you could have converted it to joules as well by using that conversion. So there's a couple different ways you could do it. Some people like to use those conversions rather than having to use Avogadro's number to convert it out, but they both will give you the same answer. Slightly different, obviously, with a little bit of rounding that you do, but pretty much the same answer. Any questions on any of that? And again, this is a measure of stability. The higher this number is per nucleon, the more stable that nucleus is. So that's another way, in addition to the N to Z and the even and even, that you can kind of measure stability if you're comparing two nuclei together and want to see which one's maybe more stable. Any questions on that there? All right, so why don't you try one then, maybe? Actually, we'll look at it this one first. So as I just mentioned, the greater the nuclei, nuclear binding energy per nucleon, the greater stability. And it actually peaks out right there at iron. 56 is actually the highest in terms of stability. And most of our stable nuclei do fall in this range in terms of binding energy, and kind of outside of that, fusion will get us into that more stable, or things will go through fission if they're outside that area to try to get them into this kind of stable area as we go through it. All right, so why don't you give one a go here, calculate the mass defect in the nuclear binding energy in mega electron volts per nucleon. Now let's do both, and joules per nucleon. And I'll give you your proton mass is 1.007825 AMU. And your neutron is 1.00865 AMU. All right, so calculate the binding energy per nucleon in both ways for our carbon-16. Carbon is still number 6 on the periodic table, hopefully. Okay, let's take a look. So again, we're going to figure out protons, neutrons, as we need to figure out our mass defect. So we do know, obviously, we have 6 protons here. Our mass number, which is 16, minus 6, which is our atomic number, gives us 10 neutrons. So we could calculate our mass defect here by basically taking 6 times our proton mass plus 10 times our neutrons mass, and we want to make sure we don't forget to subtract it from the actual mass of our isotope, which I forgot to do a second ago. All right, so if we do all that correctly here, we will end up with Looks like a mass defect of 0.1187. Again, this is going to be converted into energy. And again, as I mentioned, you could go into Einstein's equation, you could use the conversion. So since we're going to do both units here, I'm going to just roll with the conversions here. So 0.187 AMU. 1 AMU there is going to be 931.5 mega electron volts. So that will directly convert me into where I want to be maybe. That's going to give me about 110.6 mega electron volts, which at this point I can divide by the nucleon, which is really our mass number, which is 16 in this case. And that would get us to basically 6.913, we'll call it, mega electron volts per nucleon. First off, any questions on that calculation there? Once I have it here, since we're looking for joules as well, I'll do that conversion, just convert it out from here. And in this case, 1 mega electron volt is 1.602 times 10 to the minus 13 joules. And that's that conversion we saw on the other page. So if I do that there, going to give us approximately 1.11 times 10 to the minus 12 joules per nucleon. Yeah. And this guy. Any questions on either of those? Again, you could have obviously went into equals mc squared, then divided it by Avogadro's number to the 26th, which would get you to joules. You then could divide it by the nucleon, which should get you there, and then obviously you use a conversion to go from there to there in that case, yeah. Any questions on that there? All right, one last one to finish out the day here. Happiness, last example, yes. All right, let's do it. All right, here we go. Let's do our, we'll use those numbers there. Calculate the binding energy per nucleon. For iron 56, we'll just do mega electron volts per nucleon here to finish it up. And iron, I think, is still 26 on the periodic table, I hope. Okay, again, we're going to start with our mass defect and our protons and our neutrons. So the atomic number here obviously would be our protons. We're going to take 56, which is the mass number, minus 26, gives us 30 neutrons in this case. So starting with our mass defect here, we're going to, and sometimes it is abbreviated, which like a delta symbol sometimes, and obviously sometimes just an M. We're going to take our 26 times, we'll use the number that's in this problem here, 1.00783 AMU, plus 30 times our neutron, 1.00866 AMU. And then we're going to subtract it from 55.93494 AMU. That's going to give us a mass defect, which again is going to be that mass that's going to be converted into energy through this process. And we're going to get here. Looks like 0.5284 AMU, which since we are looking for a mega electron volts, so might as well just again use kind of the conversion part of it. And that's going to give us 1 AMU is 931.5 mega electron volts. So we will times that by 931.5, going to give us a 492.2. We're going to divide it by the nucleon, which in this case is really the mass number, which is 56 nucleons. Going to give us a binding energy of 8.790 mega electron volts per nucleon. First off, any question on the calculation there? All right, so to finish up on, as I mentioned, we can use our nuclear energy binding energy per nucleon as a symbol of stability. This is iron 56. Earlier we calculated a second ago 6.913 mega electron volts per nucleon for carbon 16, I think it was, and originally we did 7.780, I think, mega electron volts per nucleon for fluorine 19. The one that's the most stable is iron 56, just like we saw on that chart. It has the highest nuclear binding energy per nucleon. In this group, this guy would be the least stable of those three because it has the least nuclear binding energy per nucleon. Any questions on that there? All right, we're going to lay it up there for